Jai Hind everyone. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. Welcome to this class of Optical Communication. In this video lecture, we will discuss the concept of skew rays, and after that we will discuss electromagnetic mode theory, which is required for the optical propagation. This theory is also known as the wave theory. So main contents of this lecture will be meridional ray, then we will discuss the skew ray. Basically in this video lecture we will discuss the concept of skew ray in comparison with the meridional ray, or we will see the difference what are meridional ray and what are skew rays. Then we will discuss the electromagnetic wave theory required for the optical propagation. Then we will discuss modes in the planar guide. Then in the end we will discuss the concept of phase velocity and group velocity. So now meridional ray and skew ray. Basically in the previous lecture we have studied the light inside the optical fiber is propagating, and principle used is total internal reflection. Now the light rays which are propagating inside the optical fiber can be classified or can be of two major types. One type is known as the meridional ray, and second type is known as the skew ray. The main difference is the meridional ray, let's say this is the fiber, this is the axis of the fiber. The meridional ray cuts or pass through the axis of the fiber while propagating through the fiber, whereas this skew ray, which is generally observed through the cross sectional view, the light is propagating in this way. So at this center we have the center of this fiber, or we can say the axis. So this is the meridional ray and this is the skew ray. Okay, so the main difference is the meridional ray cuts or pass through the axis of the fiber while propagating through the fiber, whereas this skew ray follows a helical path. Skew rays follow the helical path and it does not cut or cross the axis of the fiber. Few more observations can be done here as this: the distance traveled in a single reflection is more in the case of meridional ray, whereas the distance traveled by this single reflection in the skew ray is less. Distance traveled per reflection is less in the case of skew ray, whereas more in the case of meridional ray. Whereas the interaction with the core cladding interface is more in the case of skew ray, so there will be more attenuation as compared to the meridional ray. So these are the few general observations about the skew ray and meridional ray, and this skew ray is generally represented in terms of an angle gamma, which is the half of the angle of the reflection. So this gamma, so generally there is a factor cos of gamma, so anything can be represented for the skew ray in terms of this gamma angle, which is the half of this angle of reflection. This is the complete angle of reflection, and half of this angle of reflection is angle gamma. So the anything that is available for this meridional ray can be calculated for the skew ray in terms of this parameter gamma angle through cos of gamma. So These are the some basic differences. That is, it cut or pass through the axis of the fiber, whereas the skew ray follow helical path and does not cut or pass through the axis of the fiber. Comparatively, more distance is covered per reflection, whereas in this case of skew ray, the distance covered is less by the per reflection. Here the number of reflections are less, so attenuation is also less. In this case, the number of reflections are more, so the attenuation is also more in the case of skew rays. Moreover, in the case of skew ray, it changes the plane after every reflection. That is, skew ray does not lie in the same plane after each reflection. So these are some basic differences. So as discussed, these are the views shown for a skew ray, and skew rays can be better observed through the cross-sectional view. So these are the skew ray observed through the cross-sectional view in an optical fiber cable. As discussed, this skew ray follow the helical path, and moreover, skew rays does not cut or pass through the axis of the fiber, and moreover, skew rays can be represented in terms of an angle gamma. So this is the cross sectional view. So this is the one ray of light. These are the different rays of light. So this is the reflected angle. This is the angle of reflection, and this angle gamma is the angle which the axis of the fiber makes with the reflected ray. So from this diagram we can see that this angle gamma is nothing but it is half of angle of reflection. So if we are given with the angle of reflection, we can calculate this angle gamma, and anything and everything can be represented for the skew ray using this parameter gamma, or in terms of this parameter gamma. These are the various characteristics that I have already discussed. It does not cut or pass through the axis of the fiber. Skew ray follow the helical path. Higher attenuation is observed in the case of skew rays because the number of reflections or intersecting points are more in the case of skew ray, and comparatively less distance is travelled. So these are some basic observations or characteristics of the skew ray. One more point that we will also see with the help of numerical. The acceptance angle in the case of skew ray is greater than or larger than the acceptance angle for the meridional ray. That is, acceptance angle for skew ray is greater than acceptance angle for the meridional ray. This is the numerical for comparison purpose. As discussed, anything for the case of skew ray can be represented in terms of angle gamma through the factor cos of gamma. So if you will see the derivation, the relation as sine of theta as for the skew rays, which is this is nothing but the numerical aperture for the case of skew ray. So it is nothing but numerical aperture multiply by the factor numerical aperture by cos of gamma, or we can say that sine of theta as into cos of gamma will be equal to normal numerical aperture. So normal numerical aperture for the meridional ray, numerical aperture is given by sine of theta a, or we can say that theta a equal to sine inverse numerical aperture. And from this equation we can calculate acceptance angle for the skew ray as sine inverse numerical aperture over cos of angle gamma. So numerical aperture for an optical fiber is 0.4. So we have to calculate acceptance angle for the meridional ray, that is theta a equal to sine inverse numerical aperture. Numerical aperture is 0.4. So acceptance angle is 23.6 degree. Whereas for the case of skew ray, the acceptance angle is given by sine inverse numerical aperture by cos of gamma. Numerical aperture already given there 0.4, and we are given the change of direction after 100 degree reflection. That means we are given with angle of reflection. Angle of reflection as 100 degree, and we have studied angle gamma is half of this angle of reflection, so it is 50 degree. So putting this angle gamma as 50 degree, we can calculate acceptance angle for the skew ray as 38.5 degree, and by comparing we can clearly see the acceptance angle for the case of skew ray is greater than the normal acceptance angle for the case of meridional ray. Limitations of ray theory. Basically, ray theory is an approximate theory, and it can be applied only when the dimensions of the optical fiber are sufficiently large. Dimensions are sufficiently large for applying the rule of geometric optics. So these are the few limitations of ray theory that we can overcome with the help of wave theory. Okay, so using wave theory we can overcome some of the limitations. So electromagnetic mode theory, as discussed, to overcome the limitations of ray theory we use wave theory, where the light is considered as a wave, and like the electromagnetic wave where the electric field or magnetic field component propagates through the metallic waveguide, in the similar way in the optical fiber cable the light is considered as a wave and its field component, that is field component of light, propagates through the optical fiber cable, and we can derive the equation similar to the electromagnetic wave. So to study the electromagnetic mode theory we use the Maxwell equations. Fundamental Maxwell equations of electromagnetic mode theory are used here. So this is the first equation, del cross E equal to minus curly B by curly T. This is Faraday law. Del cross H equal to curly D by curly T. This is Ampere law. These two are the equations by the applications of Gauss law. By the application of Gauss law in the electric field and in the magnetic field. This is the relation between the two through the medium parameters, permittivity and permeability. So we can derive the wave equation, wave propagation equation for any field component by taking any of the equation and taking the curl of that equation. In the previous we have shown these two equations. We can take the curl of any equation and putting the value from the second equation. So here we are taking the curl of equation on both sides and putting the values, this one, and then we apply the vector condition, this one. So left hand side becomes this one. So this is the wave propagation equation for the electric field component. This is the wave propagation equation in terms of electric field component. In the similar way, we can have the wave equation for the magnetic field component as curly square h by curly t square. In the similar way, we can have the wave propagation equation for the field component of the light. So this is the equation for the light, and this is the velocity of the light, velocity of the signal wave propagating, whereas c equal to 1 upon mu naught and epsilon naught under root. So the necessary condition for this wave propagation is phase shift or phase change. Whenever there is a phase shift or phase change, only then the wave will propagate. That's why the velocity here denoted is known as the phase velocity. It's simple. The lambda beta equal to 2 pi by lambda. Whenever there is a phase shift of 2 pi, the distance covered will be lambda, one wavelength. The wave propagation equation can be represented in any of the coordinate. We can also represent in the rectangular coordinate. We can also represent the wave propagation equation in the cylindrical coordinate. Then we can find the solution of that wave propagation equation. Generally, the solution is represented in the exponential form, where this k is the wave propagation number 2 pi by lambda, and this r is the generally the direction vector. This k is the vacuum phase propagation constant as discussed. Whenever there is a phase shift of 2 pi, the distance covered will be lambda. This is for the vacuum, and in case of any medium, it will become, let's say in the core, it will become n1k. So beta will be there as n1 into k equal to n1 into 2 pi by lambda, where this beta is phase factor. Then we will discuss modes in a planar guide. Basically, we have studied optical fiber as a waveguide. Then planar guide is basically the simplest form of optical waveguide structure. In the simplest form, we have a inner layer refractive index n1, outer layer refractive index n2. So basically we have a glass plate with dielectric refractive index n1 and is sandwiched between two layers of lower refractive index n2. Okay, so we have a inner layer n1 that is sandwiched between the two layers of lower refractive index n2, where n1 is greater than n2. This type of waveguide structure is known as the planar guide. So in the planar guide, simply we have a slab of dielectric refractive index n1 sandwiched between two regions of lower refractive index n2. As this is a simple structure, so the modes existing inside the fiber will also be the simple modes. So simple modes will be generally the transverse magnetic modes or transverse electric modes. So in this planar guide, generally the TEM and TM mode exist. Mode means inside the fiber there is a field component. That field component will make a particular type of shape, pattern or distribution inside the fiber, which is termed as the mode. So along with this, there will be a subscript to denote the order of the mode. Let's say it is denoted by small m. So small m, it denotes the order of mode. This is the propagation shown inside a planar guide. There is a direction of propagation. As discussed, there are only transverse electric or transverse magnetic modes. So along the direction of propagation, there will be no field component. So light is considered as a wave and it propagates through the optical fiber cable, considering as a planar guide. And inside the planar guide, there are points of equiphase which together form a wavefront, and this wavefront travels with a constant speed in the direction of propagation. And this constant phase points or equiphase points travel with a velocity known as the phase velocity. So this is the diagram showing the formation of mode and distribution and then propagation of light inside the planar guide. As discussed, mode is basically nothing but it is the particular type of pattern distribution by the field component inside the optical fiber cable, and some part of the field component may also penetrate into the cladding, which is eventually lost in the form of heat or radiation. And this part penetrated into the cladding is generally known as the evanescent field. This is one observation. As discussed, we have transverse electric and transverse magnetic mode with notation small m. This m is the order of mode. There is observation, as we increase the order of the mode, penetration into the cladding increases. Penetration into the cladding increases, which is a kind of loss. Light penetrated into the cladding does not propagate through the fiber, which is eventually lost in the form of heat or radiation. So we should try to have lower order modes inside the optical fiber. As the value of m increases, penetration into the cladding also increases. And in the last we have phase velocity and group velocity. As discussed, the light inside the optical fiber may propagate as a wave. So if we have a single wave, monochromatic wave, that is propagating along the z direction, the velocity of propagation is known as the phase velocity, Vp, omega by beta. It is called as phase velocity because the necessary condition for the wave propagation is change of the phase. So whenever there is a phase shift or phase change, there is a distance traveled by the wave. So whenever there is a single wave, it is known as the phase velocity. And we can also have, in practical situation, we may have a number of waves which have similar characteristics, like maybe similar in terms of frequency. They are combined together and they form a package or packet or envelope, and that envelope travel together with a velocity that is known as the group velocity. So this is the case for single wave. And as discussed, in practical situation we may have a, let's say in this case we have two waves which have similar characteristics. For example, here the frequency is almost similar for the two waves. So these two waves are combined together to form a wave packet, and they make a envelope, there are two waves which have nearly equal frequencies. Together they may be a packet or envelope, and this envelope travels together with a velocity known as the group velocity. So this is the relation with the phase velocity, velocity of light in a particular media. In the similar way, for the group velocity, we can also have the relation as Vg equal to C by Ng, where this N1 refractive index of core, this is the group index. So that's all for this lecture. Thank you everyone. Jai Hind. This is a reference book that I have used for this lecture. Jai Hind.